Hello everyone, welcome back to Linear Modeling. In this lecture, we will talk about gradient descent algorithm. In the previous lecture, we talked about the linear regression. Linear regression is a line which will identify the relationship between independent and dependent variable. Basically, if you see in that case, there are infinite number of lines are possible. Out of that, we need to extract the single line which will find the relationship between the independent and dependent such a way we have the minimum error. So the question in the linear regression is still exists that what is the value of A and B and how can we identify the A and B values. Here is what the gradient descent comes into the picture. So first of all, let's simplify our question. We need to select the line such a way the minimum SSC. For the sake of simplicity, let me consider only the slope of a line. If slope is equal to 0, then the line is almost horizontal. So which has a very large error somewhere around here. And as the slope increases, your error is coming down. And up to certain point, and after that error starts increasing, which is what something like this. As slope increases, error comes down, again it starts increases. So as you can see that the minimum error we can find at somewhere at this point, and our objective here is to find what is the value of A and B such a way we have that minimum SSC. One of the greatest power of the calculus is to determine the maximum and the minimum value of any function of any given function. If by computing the derivative of the function, if the derivative is negative, which indicates that the slope is negative, indicates that the line is decreasing. For example, if the derivative is positive, increases that line is increasing. If the derivative is 0, indicates that the slope is equal to 0. So just a thing that we can have the minimum point or maximum point only when the derivative is 0. So what we need to find in this case is that we need to find the point at which we have the minimum point. But still there is a confusion that this is possible that both minimum and maximum point. In order to understand that what is the minimum or maximum point, we need to compute the second order derivative. Second order derivative will try to compute the next slope. Means after that point where we have the slope is equal to 0, after that point what is the slope we have. If the slope is negative, after the slope is equal to 0, indicates that line is starts decreasing. Maybe it sees that the value is the maximum point. And similarly, if the slope starts increasing as shown here, after the slope is equal to 0, indicates that my second order derivative is increases, is positive, means that the line is increasing. For example, if the second order derivative is 0, such kind of point is called inflection point. So what we are interested in this case, it is maximum point or a minimum point. So let's take this knowledge what we have, let's put it in our gradient descent algorithm. Okay, this is the function f of x which has with us, and in this point we need to identify the point a and b such a way where we have the minimum value. So this is the equation we have, and this region consists of negative slope, this region consists of positive slope, and one particular point we have slope is equal to 0. And the equation of this function is summation of yi minus y hat, also known as cost function or optimization function. As we already know that yi is estimated value is a plus b into x, just substitute the value here, and with that we will get yi minus a plus b into x whole square. And so this is what our function, which is function of a and b. So we need to find out the values of a and b. Let's try to understand that with the different values of a and b, what is the change in value, whether it is increasing or decreasing. So in order to compute that variables for multiple parameters, we will go for the partial derivatives. That partial derivatives are called gradient. So we will calculate the gradient of that function, cost function, with respect to the parameters. In this case, we have the two parameters that we need to compute. So we will calculate that cost function with respect to a and with respect to b. So if we solve that, so what is the value equation we'll get is that summation of 2 into xi yi minus a minus b into xi for with respect to a, and with respect to b, summation of minus 2 into y minus a minus b into xi. So we know the values of a and b, and for any particular value of a and any particular value of b, we can able to find that change in value, change in the cost function with respect to both a as well as with b. So once we know the change in values at each and every iteration, we can apply the mathematical method concepts to our optimization values like a and b. So a is equal to a init minus partial derivative of cost function with respect to a into learning rate. Similarly, the value of b is b initial value minus cost of the function with respect to b into a learning rate. So with this equation, we can able to find out the what is the value of a and what is the value of b, and ultimately we need to find out the convergence point of a and b. So how we achieve that, let's see. So let's say how we are having these two equations, a for a is equal to a init partial derivative with of cost function into a and so on with respect to b. For the sake of simplicity, let me consider only the slope, and same thing can also apply for the intercept too. So let's say I'm having one point here, and at this point I just want to compute the slope of a line. With respect to p, I need to find out the cost function. So if I compute that, so obviously the cost function what I got in this case is a negative value, indicates that your value is decreasing. So now what we will do, we'll take that cost function of the negative and substitute in our equation. As we substitute in our equation, we will get b is equal to b init minus of minus negative value into learning rate. So the value what you'll get in this case, it is b initial plus some positive value. Let's say if it is b is equal to 1, and the next value what you will get in the next iteration, it will become something like 1 plus 1.1 plus 0.1, which could be equal to 1.1. So we can able to find the newer value of the slope is somewhere around here. So what we got in the one epoch is that we got some jump. So we are trying to find the convergent point in this. So we try to repeat this process again and again. Now we'll calculate that the derivative with respect to b, and I found it to be the negative value, and substitute in our equation, and finally we can able to get that equilibrium point. Just showing something like here, we start here, and each and every iteration we can able to find out our convergence point. Now the question here is that what is this learning rate? What is the significance of the learning rate? Generally, the value of the learning rate is between 0 to 1. The main reason of using the learning rate is because the derivative is highly unstable. So because of that, your model might also lead to the unstable, since the small change in the derivative may have the very large values. Something like this. Let's say if we start our value somewhere around here, and we might have the larger jumps without using the learning rate somewhere on here. See, initially your algorithm seems to be converging, but not. It may not converge. Initially few iteration your algorithm seems to be converge in this process. So let's say what it happens is that initially we have the larger jumps, and we have the maybe settled to somewhere around here, and it says that algorithm says that okay, your value is increasing, and if you substitute in this equation, and maybe it moves in the negative slope region. And from there it jumps again to the right hand side and left hand side and right hand side and left hand side, and your model will be highly unstable. You will never reach the equilibrium point without applying the learning rate. If you apply the learning rate, you can able to achieve such kind of process. Suppose if you apply the learning rate, you can, even though it will take the longer times, but the convergence is guaranteed. It is good to take the smaller values of learning rate rather than the larger learning rate. If you apply the learning rate in the slowly and steady, it might reach some other point. Even though if it reaches this point in the right hand side, we are actually maintaining the smaller steps. So again, we might reach into the equilibrium convergence point much more effectively by the learning rate. The smaller learning rate, smaller the steps, and we might converge in a better way, and we can get the good optimal values with the smaller learning rate. There is one more optimizer function similar to the gradient descent, is Adam optimizer. Adam optimizer is almost similar to the gradient descent algorithm, but the small changes which makes it much more powerful algorithm. Adam optimizer generally starts with a larger learning rate. As the error is coming down, the learning rate comes down. As shown here, we start with a larger learning rate. As the error is coming down, your learning rate is keep on coming down. So with this, with the smaller steps, we can able to achieve our equilibrium point. This is the powerful approach used in the neural network, convolution neural network, logistic regression, and many more. Has very wide variety of applications with these optimizers. Hope you enjoy this lecture, and we'll continue in the next lecture on model architecture. Thank you.